When working with functions, there is oftentimes multiple ways to represent that function that can be useful. There are 4 ways that we're going to be discussing in this course. The verbal representation, which is typically a description given by words, could be just plain English text. A numerical representation, we've done this already with a table of values. A visual representation, which is going to be done with a graph in the Cartesian coordinate plane, and then you might argue that the arrow map also would fit into that visual, graphical looking representation, but we typically call the Cartesian coordinate plane visual, the visual representation. And then there's the algebraic representation, which is what the equation or the formula is there for. So you'll find at times you'll be asked to go from a verbal description to a algebraic description, but sometimes it's not always as clear-cut how to do that. So you might go from the verbal to the graph, and then from the graph you can then figure out what the equation would be. So at any point you may end up using a couple of these visualizations, a couple of these representations, or you may use all of them. You never know. It just depends on what the situation calls for. So with this example, really what I'd like to do is take you through one specific example that shows all 4 of the different representations. So I'm going to start with the verbal representation, and what I'd like to describe is a calculation for the area of a circle. The area of a circle is a product. So product means it's going to be a multiplication, and I need to describe what things you're going to be multiplying. It's going to be a product of, here's one of them, the constant pi, and the square of the circle's radius. So if I was looking at this and trying to maybe diagram exactly what's being asked, we have a product, and if I'm doing a product, I have to have 2 things to do that with. I can't just have a multiplication with only one thing. I have to have 2 elements to do that with. One of them is the constant pi, and the other is the square of the circle's radius. So those are the 2 items that will be multiplied together, and this really does tell me everything that I need to know about calculating the area of a circle. The second representation, which is going to be the numerical representation, is going to have me take this verbal description and then start playing with the radius. Start picking different radius values and then actually calculating the area. So my table is going to be, again, a t-chart like we've seen before. I will have the radius for the first column, area for the second column, and I'm going to pick some relatively nice radius values. 1, 2, 3, and 4 would be relatively nice. And if I put them into the format that I'm looking for, it's supposed to be, for example, I'd say pi, and I'm supposed to multiply that with the square of the radius. So I've picked my first radius value squared times pi, and that will be approximately 3.14. I take out 1, replace it with 2, and then I would get 12.57. Now these are all approximate values. These are not going to be exact, but for graphing, an approximation will work really well, and that's where we're going to end up going next. So let me finish the table. 3 would map to 28.27, and then 4 would be 50.27. And let's move on to the next visualization, the graph, our next representation. So for 3, I'm going to set up a Cartesian coordinate plane, and what I'll have you notice is that I'm just going to draw the first quadrant because all my values in the table are positive. I really don't see any reason why I'll get anything negative. It doesn't make much sense to have negative area or to have negative radius. So first quadrant should be really all you need. 1, 2, 3, 4, 5. So along the horizontal axis, this is where I'm going to put the radius values. And this is the standard convention. Whatever you have listed in the left column goes along the horizontal. Whatever you have listed in the second column will go along the vertical. So we'll do the same thing for the vertical, except I am not going to go by ones, I'm going to go by tens. 10, 20, 30, 40, and 50. And I will label this as area. So let me take the data from our table and let me plot it. I'm going to use green. 1 maps to about 3.14, 2 to about 12.6, 3 is about 28, and then 4 goes to about 50. And it's really important that you take the time to draw your Cartesian coordinate grid as evenly spaced as possible. If you don't have things evenly spaced, then you have a distorted view of what the pattern really looks like, what the shape of this curve is really going to look like, because it's supposed to be a curve, not a straight line. So what we'll notice here is that these 4 points have this kind of increasing curve look to them. But I also recognize that 1, 2, 3, and 4 are not the only radius values that I could have used. I could have used, say, 1.5. I could have used 3.7. Now, these would have all been potential radius values. So to help illustrate all of the potential radius values and not just the ones that are in my table, I can connect the dots. And I'll draw a curve. And on the right side here, I've drawn an arrow because I could certainly have radius value that is bigger than 4. So this would continue beyond the viewable window that we have. And then going backwards to the left of positive 1, to me it doesn't make sense to have an area or a radius of 0, because if you have a radius of 0, then you don't actually have a circle at all. So I'm going to put an open circle there just as a placeholder for me to then connect the line the rest of the way to represent all the other areas that would go with radius values that are between 0 and 1. And I'm going to label this as capital A. And then for part 4 of our representation, we're looking for making a algebraic representation, some kind of formula equation. So we're going to do a function definition. That will be our algebraic representation. So I've already named this. I've named this capital A, and I think that's appropriate because the purpose of this function is to calculate area. So capital A is a pretty natural name for it. And when I think about the domain, I think about what sort of values are appropriate for the radius, because that's the first column that represents the first set. And we've already said negative doesn't make any sense. And we just made a claim about 0 not making any sense. So the domain needs to be everything that's positive. So that would be the interval 0 to infinity. And these are going to be the values that map to real numbers. And this is going to be given by the equation a of r equals pi r squared. And that gives you the 4 representations for this area calculating function.